The next talk will be by Aahana Aggarwal, who will talk about from discrete to dense, exploring lattice triangles in moduli space. And how do you like people to ask you questions?
Yes.
How do you want them to ask questions? Do you want them to type in the
Uh,
chat or speak, or what do you want them to do?
Anything is okay. Anything is okay.
Okay, so go ahead.
Hi everyone. My name is Aahana Aggarwal, and today we'll be exploring lattice triangles. So, what are lattice triangles? Lattice triangles are triangles with vertices on integer coordinates, like these. So we study moduli spaces of lattice triangles. Moduli space is a map which classifies every single triangle up to similarity. Think of any single triangle and you can place it in the moduli space. We consider some constraints while considering a labeled moduli space of triangles, which considers the vertex order. So a triangle with vertices ABC is not the same as the triangle with vertices BAC. Now, in a labeled moduli space of triangles, we can see six similar sections. These are not necessarily same, but these are similar. When we consider only one of these sections, we obtain the unlabeled moduli space of triangles, which does not consider the labeling. So you put the vertices in any order and it's the same triangle. But the question is, what triangles appear as lattice triangles? Isosceles triangles do, right angle triangles do, scalene do, obtuse angle do, but there's a famous result that equilateral triangles do not appear as lattice triangles. This is because an equilateral triangle requires its height to be a multiple of root 3, which is an irrational number, and no lattice point exactly lies with an irrational number. To prove this, we consider a vector. Suppose there is a vector at point A with coordinates x1 and y1, and we rotate it by 60 degrees from both sides to get to point C. Now, the coordinates for point C would be what we obtain from sine and cos of that 60 and 30 degree angles, and these wouldn't have a exact lattice point unless both x and y become 0, which would result in a degenerate triangle. So lattice triangles cannot exist as equilateral triangles. But the question is, can we approximate them? Yes, we can. So consider a triangle with three coordinates 0, 0, 2g, 0, and 0, g root 3. We take this coordinate 0, g root 3 and we take the floor of g root 3 to obtain another lattice point D. Here we use the Dirichlet's approximation theorem to do so, such that the modulus of g root 3 minus the floor of g root 3 is something less than epsilon, where epsilon is something greater than 0, which is a very, very minimal difference, but we can obtain a lattice point close to point C, which is not on the lattice. This graph just shows that there always exists a value for g root 3 such that it is always existent no matter how high or how low the value is. Now, we also consider the density of lattice triangles in the moduli space. What do we mean by density? Density is just this. A set is dense if every point in the space can be approximated arbitrarily close by the other points in the set. So, to prove density of lattice triangles, we take a huge box of points and we of triangles and we approximate. We use the pigeonhole principle to approximate a value m. Using the Dirichlet's approximation, we modify this Dirichlet's approximation to consider two simultaneous constraints instead of just one constraint, from which we obtain that there must be 2 points inside one box, which gives us the approximation that some number m must exist such that the fractional part of mx is less than epsilon along simultaneously while fractional part of my is less than epsilon. Here m, x and y are the real numbers. These are some plots that I did in Python, which shows this one particularly shows a moduli space of 100,000 lattice triangles in a 10 by 10 grid, which shows that there are some empty spaces here. But what we notice is that as we move forward, we see that as we increase the number of points in the same bound, that space starts filling up. As we increase the bound, if we keep the number of the lattice points same and we increase the bound, the same thing happens, which just tells us that lattice triangles are dense in the moduli space. Next thing is, this is a hexagonal plot of a million points in 100 by 100 bound. If we zoom, okay, when we see this color graph, we can see that there are some discrepancies in the center. In the majority of the part, it's bluish greenish, showing uniform distribution. But on the sides, we can see there are some yellow sections. So when we zoom on into them, we see that there is some high count, above 1,000 triangles lying in these small hexagonal areas. This is a plot of the moduli space divided on the basis of their triangular angles. Same thing we observe if we notice at the vertices of this so-called triangle, there are some high density points like these. So now we consider the distribution of lattice triangles. When we see this figure, this is a moduli space of triangles that we consider. This is the black space is the moduli space of triangles that we're considering. For now, we'll just consider section 4 and we'll count the number of triangles in that section. According to our expectation, lattice triangles should be uniformly distributed. They should be equidistributed, and there should be 25% of points in each of the sections. So are these equidistributed? They're not. We find that only 23% of the points lie in there. Though that may not seem like a very high number, but it is significant when you're considering about 100 million points. This central region, red region, is slightly underrepresented. This can also be backed by the theorem found in 1969 by Langford, which states that there's about a 3/4 chance that an angle lying in a triangle is an obtuse angle, which supports this because the triangles lying in the other three sections are tending towards obtuse angles, while in the center it's tending towards a more acute triangle. The key results from this presentation are that equilateral triangles cannot exist as lattice triangles. Lattice triangles are dense in the moduli space, and lattice triangles are not equidistributed. Thank you.
Okay, thank you. So are there any questions for Aahana?
I see a question in the chat. How do we pick those triangles randomly? I am not really sure I understand. If you could please elaborate more on the question.
I had a similar question actually. I was wondering yeah, what's the distribution of the triangles? Like how are you? What's your prior distribution?
Oh, so we are just considering all the triangles that you can probably imagine, all the lattice triangles, or all the triangles that exist in a particular bound, and we're plotting them into the moduli space. Moduli space is just a map with all the triangle shapes that exist. And then we are doing the operations that we need to. Like we're considering the distribution. So in that region, in the red region that we were considering in section 4, we're only considering the triangles that so in the very, very center of the moduli space, there lies the perfect 60, perfect equilateral triangle, which we say is not possible. It doesn't exist. So all the triangles on the very side of the moduli space are degenerate triangles. So the whole thing ranges in between there. So we find that in the center section, the observed count is less than what it should be. It is expected to be 25%, but it is observed to be 23%, giving us the fact that lattice triangles are not actually equidistributed. They tend to move or form shapes that are more obtuse angled rather than perfect equilateral shapes.
Okay. Are there any other questions? Okay, well, thank you again.